Here is the compiler for the Elna programming language again. Today we will probably do a few different things depending on how much do I have. Last time I tried to change the stack allocation for the local variables so that I don't assign stack offsets to local variables just after the parsings, but that I do it in a later stage before the assembly code generation. But I recognized later that my approach was completely wrong because I tried to change the allocation for specific operations like multiplications, and of course it won't work since I can just change the stack allocation for operations. I also, for example, for binary expressions, I also have to change it for other things at the same time. For example, for assignment, so that I can assign a value to this variable before I can multiply it with something. So I changed after some struggling. I changed my my approach and just changed the calculation of the stack offset for some variables and later for all the variables. So now I really have a stack allocation, stack offsets are assigned later to the variables. It is not complete yet because this is done. So if we look at our stack, allocate stack, I think. So I still allocate a static stack size for each procedure, 200 bytes, because we still need to migrate other variables to local to dynamic allocation. So for example, that arguments and temporary variables are also allocated dynamically, but currently we still need this static stack, for example, so we can save the parameters of the procedure, because the parameters are passed in the registers and we need to preserve them if we want to work with these parameters, and they are also needed for arguments, because arguments of a procedure can be expressions, and we need to calculate all these expressions in the arguments and then save them to temporary variables and pass them to a procedure call later. So it still has to be done. But at least for variables, so the first 130 bytes, as it seems, are reserved. It is a bit too much. I think I already moved so the storage for the arguments and parameters of procedures were at the end of this static stack, but after I don't have to reserve space for the temporary variables, we can actually reduce the size of the stack of this static stack, and I think the last byte that is reserved is 56, so it should just work if I begin my not reserved stack with 60. Let us try to compile it. And it works as expected. If I, for example, change it to 56, it will probably work, or maybe not. I hope that not, because it will overwrite stack of other things, so it crashes. So 60 should be the right value, and after we visit the body of the procedure, this temporary variable counter will contain the last stack value that is used, so we can actually save this stack value so that we allocate the top part of the stack, so we can allocate it dynamically. We can try it. So we generate here this allocate stack instruction which actually allocates the stack, and what we can do, we can add a new line here, and we can just so I have specific functions currently. Tell instruction set operand, I think, and we want set the operand in the instruction set instruction. We want to set the first operand. The operand type would be RTL operand immediate because we just set an integer here, and the value would be temporary variable count, and the last argument is 0. Operand length, since it is not a string, it is 0. And the same we want to do for the return instruction. Actually, it should be renamed. It should be called the allocate stack. Probably we should try to do it just in a moment. So I can finish this thing. We also say set the stack size as operand for this return instruction. It should compile as well. And then we go back to the point where we generate code for this instruction, and we replace this write z procedure with a printf. So I still need at 8 bytes to save the return address and the frame point. So we can actually start with the frame pointer, because if the return address is saved late, it isn't actually a problem. So there will be just some space between the frame point and the return address. So, but we need to get the value of the stack. I actually have this argument count variable, which should actually be called just argument count and not argument count 1. So let us rename it. We actually should move this handling of these two instructions of return instruction and allocate stack instruction out of this function, because these two instructions are something special in the sense that they generate multiple instruction and not just a single assembly instruction. So let us finish this one and we return argument count. And we get a weird error. Argument count. So if I look at the assembly, it prints minus 208 after the stack pointer. Oh, I always forget this. Printf does buffered IO probably. But our other instructions are written without buffered IO. So yeah. And then we output the stack later than other instructions, and it shouldn't be the case. So what do we want? We wanted to start with the address of the frame pointer, and we can save the frame pointer. Let us reuse for now the argument count variable, we will change it in a second. So basically we will call a tail instruction get operand from the we can do it here, can we? Do we have the instruction? We don't have the instruction at all. We can't read the stack size here. So we need to move this this procedure outside of procedures. I mean to move printf out of this procedure. So where it is used, I have already a special case for writing the labels, I think. Let us split the screen so we can better search. We go to the top of this procedure and just look where it is used. Exactly. I have already a special case for writing the labels if the instruction kind is a label, and we just need to add another cases. We can copy them from here. This is the first case, and this is the second case. Then we want to go into this procedure at all, and what we actually want, we want just to write the prologue in this branch and the epilogue then in this branch. We do not need to set the argument count since, I think we need, yeah, let us just do it here once. So theoretically we do not need these two branches anymore, so we can remove them. And here we have now the instructions, so we can get the value of its operand, and we can then print it inside the prologue. So we take the operand value and put the frame pointer at this address and see what happens. So that's fine. I wonder how the stack is deallocated. It's a bit yeah. I haven't replaced it in the epilogue, but it still works. Yeah, whatever. So operand value here as well, and we need it when we read the stack pointer again, frame pointer. So basically here, I suppose. The next one will be the return address. So the return address is operand value plus 4, and here as well, and we change this 204 to an I, and here and now I will replace with this E with 204 and hope then it fails, because it kind of should fail. Yeah, okay. So that does something at least, and everything that we need is to set the stack size so we can finish the stack. And after we have written the return address, we just set the stack pointer to operand value plus 8, and we do the same here, and we can replace this 208 with I, and here, and we need this value twice. And I think I have the specifiers in the wrong order. So the first one would be, it doesn't, these two, operand value and operand value plus 4, the order doesn't matter actually, because they are just swapped, but probably they should be in the same order in the prolog and epilogue. 1 second, we will look at it. So first we increase the size of the stack, and as the last operation we move the frame pointer to the old position of the stack. So the first and the last values are operand value plus 8. Then we save the frame pointer on the stack. This is operand, no. Then we save the return address on the stack. This is operand value, and then we save the frame point on the stack. This is operand value plus 4. And in epilogue, first we restore the return address, and return address was in, it was the first one. Yes, it was the first thing that we saved. So it will be operand value 8. This is correct, operand value. Then we restore the frame pointer. The frame pointer was the second one. So stack size, return address, frame pointer. This was operand value plus 4, and then we decrease the stack size again, so it is operand value plus 8. Okay, that seems to compile. I wonder how my stack looked before. Let us just look into the previous stage. CLL, the stack was a bit smaller, so we look for the prolog, and we saved return address with a bigger offset. So and then the frame pointer. So I will just keep the same structure, and I will add plus 4 here and remove it from here, and here we need to swap these two values too, and it probably will still compile. Okay, how long is this line? It should be broken. I hope my parser can handle this. Yes, it does. And at this point we implemented actually a feature. So since previously, this is the previous stage of the compiler, the stage 16th. Previously the stack was static, so we always located 144 bytes, and it means that that each procedure cannot have as many local variables as it wants, because the variables will overflow the stack and will overwrite other things in the memory. But now we just assign offsets to the local variables, and then we set the stack size as big as we want. It is of course still limited, but it is limited now not by the compiler but by the size of the stack that the operating system allows. And now we can just document this thing as well and write that the number of local variables is not limited. If we have more variables, the stack grows, and then we have less variables, then the stack is smaller. Let us actually look also into the assembly code for this stage. So this will be in build valid stage 17 CL, just to, for example, here string length allocates 80 byte long stack. This adds add string procedure allocates 84. So we really see that each function allocates as much stack as it needs. Okay, the other thing I've seen here also this argument count one thing. I will rename this variable here as well. This one is basically, it was a hack. It was what I told in the beginning, that I just got some variables that I tested with this dynamic stack. So I just renamed to some variables to variable name +1, so I can say, okay, the variables that end with the 1 aren't allocated, not the static offset is used, but the stack is calculated later, and these variables with suffix 1 are just coming from this experiment basically that is now finished, so we can rename them back to their normal names without a number at the end. I'm also going to save the current state so I can revert if needed. And since the compiler gets more complex and gets more features, we always have some things that weren't possible in the previous stages but are possible now, and we slowly need to fix these things so that the code of the compiler itself is a bit nicer. And the one thing that I want to do is renaming. I had somewhere these info types. So the type starts with the underscore. It was required in the previous stages of the compiler, but it isn't needed anymore. So I want to give these variables, this type, a new name. First, they should get the ELNA prefix. And I also think that I want to give them ELNA symbol prefix, because info is basically, it is symbol info. So we will take, for example, this variable here, and we will rename it into this is the wrong beginning, because if I look for info, I will also find things like type info and parameter info. So we actually want to begin with type info, for example, and we rename it into ELNA symbol type info, and we just will look for other usages of this type. The type info is done. We go back and look for the procedure info, for example. That shouldn't be that much. So Elna symbol procedure info. This procedure info size generally these size procedures are automatically generated, so size is just prepended to the name of the type. This is a temporary solution, so I have a feature in mind how I want to implement a size of operator in my language, but it will come later, so it isn't available currently, so I generate these procedures automatically. Symbol procedure info. I just want to rename a few things each time, so slowly we can have better names in the compiler, because it wasn't possible in the beginning, so we need to adjust the code a bit as we go with implementing new features. Then we have parameter info for procedure parameters, and we also call it Elna symbol parameter info. No. And I think that was it. And the last one I think is this temporary info. So temporary in this case means a local variable. Some languages call them temporaries. For example, Smalltalk. So it's just a bit shorter than local variable. I could call it just a local, but well, I called it temporary. Elna, what was the symbol? Temporary info. Probably that was it. Oh, this wasn't last. We have, of course, the base type. the info type, and it will be more fun to search. So this one would be ELNA symbol info. This is a different thing. Temporary info. Info kind type info, procedure info. Okay. That compiles now too. This info kind is also a bit stupid name, so it should get the same prefix basically. Info kind is okay, but it should have this ELNA symbol prefix. So let us do it as well. ELNA symbol, I said, or let us save the current state of the code. Then we rename this thing, because there can be a few places where it is used. I think now probably that won't be that many. We just have 5 kinds or so. So let us just add this prefix, and we go through the usages. Here it's fine. That's enough renamings for today. And the last thing that I want to do, I want to try to introduce error handling. We won't do a lot. We will just add the basic types, so actually just the first steps towards the error handling, and we will pass a list of errors. We will begin with the parsing step or pass. To each parsing function, we will pass a list of errors, and so the parsing procedures can add errors to this list. Let us go to the last type definition, or probably before we begin to define the enums. This is still an enum. So here it is, and here we define a new record, and we call it ELNA error list. It is a record, and this record should have a pointer. It should have a pointer to the first element in the list. We call it just first, and it will contain a pointer to the last element of the list, so we can append the errors more easily. And now we have a base, and now we need a base type for the errors itself. We will do it the same as I do it for other types that are actually enums. So I want to distinguish the errors just with an error message. Probably they won't have an error message at all. They will have a kind, so there will be limited amount of kinds of error kinds, and we will print the message later based on the kind. And to print an error message, we will just save additional information together with an error, and we will have a union of errors that can have different information appended to them, but it will come everything in future. For now, we just will define an ELNA error record with a single field. So the current tokenizer doesn't even save the text position, so we cannot print line and column. First we need to save the source code position in the tokenizer, but I will do it on another day. No, that's wrong. So our error list is a list, and this structure contains the first element, but each error should contain also a reference to the next element in the list. So we don't save the kind here, but we save this, we add this next pointer. I actually think I can call it pointer. Will it compile? No. The previous stage probably doesn't understand other types than Word, and each stage should be able to be compiled with the previous stage and with itself. It's basically how I test the compiler currently, so it should be able to compile itself. And we begin with the compiling in this compile procedure, and the first thing that is called here is this ELNA parser module declaration thing. and let us add a new variable here, error list of type Elna error list pointer, and we will allocate some memory for it. As I said, I generate a procedure for each type that gives us the size of the type. Malloc map returns zeroed memory always. I'm not sure whether malloc does it. So let us just initialize the list to 0 so that we assign error list. We assign nil to the first element and we assign nil to the last element, so we don't have any garbage there. And now we pass this list to the module declaration parser, and we will look for this procedure. It should parse the program keyword at the beginning, and I should learn to type. Okay. It allocates space for the module declaration and skips this program keyword with a semicolon. I actually want to get rid of the semicolons at the end of declarations and only keep them between the statements, but it is a topic for a different day probably. So what do we need? We expect that after we skip the comments, I should handle comments better as well. I allow comments only on specific places. But actually, if we read this thing, token kind should be program. If it's not program, then we have an error. So if token kind is not program, I have to look up how the token is called. So it is underscore program Elna Lexa kind program. Then actually we can also add an else, because we are going to continue to parse only if we encounter a program keyword here, only in the success case. Otherwise we will just return nil, I suppose. Let us add a variable parser error of a pointer type to Elna error. What is just was it just Elna error? Elna error Yes. So, and if the first token in the program is not a program keyword, then we allocate an error, elna error size. We assign the next element of this error to nil, or we assign nil to the field next, and then we need to append or to set the list to this variable. So at this point we have just started, we know that that the list is empty, and we need a parameter here. What was it? Parser error list of type elna error list, and we can assign error list first to this error, and we can assign error list last to this error as well. This is the reason why we need some error handling, because current errors are very cryptic, or basically we don't get any errors. The compiler just crashes and we don't know what is wrong. Token kind, Alexa kind program. Error list of type pointer. Oh, yeah, of course. Actually, we can't just return nil from here. I can do it with this procedure, but in the later procedures we do not want to overwrite the tree that is already parsed, I think. So we just append an error. I mean, the caller can the caller can just check whether the error list is empty, and if it is not, then yeah, then fail. So we are going to remove this return nil and end the return statement before returning the result, and we need to move this semicolon, and then we can try once again, and it still fails. Okay, let us remove some parts of code. Okay, now it compiles. So it isn't happy with some of these procedures. With some of these statements. At least we dereference this. Oh, of course. We need to reference parse the error first before we can access a field on it. And it compiles now, and we can get it in again. And now it compiles. So I just write it in here as if it is a single possible error in the compiler. Later, of course, we will extract this code into separate procedures, so I can just call add error or whatever, so we can handle it easier. But for now, for this first step, we just want to handle the first possible error and probably print it to the screen, which will be a bit difficult, I think, because we need to write test there. But now we can, so we call here this compile procedure, and it doesn't return any result. But we can let it return a Boolean value. Will Boolean compile? Probably not. The previous stage doesn't support it, as it seems, so we call it a word for now. And we say that if error list is Leah, then we set this compiled to true, because it the compilation is then successful, and if it is not 0, then we have an error, and we just return this compiled thing, return compiled. The other stuff will fail then, so we only call this if we do not have any errors during the parsing. So we say if compiled, then otherwise we just return this compiled variable if it is an error. Later other passes will also return a status whether the pass was successful or not, so that we can report errors. So the compile procedure now returns an error, and we go to the main block. Oh, we still have a main function. And can I call procedures in the if expression? I hope so. So if compilation was successful, we return 0. If it is not successful, not return 0, we exit with the status code 0. If it is not successful, then we exit with 1. That looks fine. So I think actually we have something we can test. I don't pass error to this compile function. I probably should create the error list here or output the errors later. but it doesn't matter. Let us just test it. So we exit the compiler and we're just going to create a new stage. So we copy boot stage 17 into boot stage 18 and we try to compile it quickly. And now we open the newly created stage 18 and we just replace the program keyword with an identifier and try to compile it, and the compiler exits. This is not exactly what I expected. So the compiler fails. Now it's probably, the reason why we get this error is probably how the current build pipeline is implemented. So the program exits with 1 and verify build boot stage 18. It has this CLS file and it is empty because it exits. So I can just try to call it directly. So we are going to take the compiler from the previous stage 17 CL and we will pipe the stage 18 into this compiler, the source code of course of the stage 18. It is executed, it outputs nothing because we break just after the parsing, and if I change the error code then it is 1, and we can just do a small test. We change this 1 to 4, compile it again. Call it, and now the status is 4, so we report an error. Yeah, and I probably should improve the build pipeline a bit, but if I write to the standard error stream, then the error messages should be actually printed. So but I shouldn't try to compile the assembly files if the compilation fails. I actually don't know why rake doesn't stop. Probably, yeah, I should look into the build stage, because currently the compiler exits with non-zero status, but the build pipeline still continues and it should break at this point. There is some kind of mistake in the rake file. I should probably look into it later, but now we have a few basic types for the errors. We return an error status code if we have a parsing error in the file. because for example, if I do the same change in the 18th, yeah, okay, then I do the same stage, then if I introduce the same bug with this program keyword in the 70th stage, then it will be successfully compiled by the 16th stage, because the previous stage doesn't look at this program keyword, it just skips the first keyword that it sees in the file, but I cannot test it because in the second step the compiler compiles itself, so the stage 17 compiles itself and it will fail, but actually we have this error handling at least for this first possible error. We can remove the stage 18 again since we do not need it anymore. We can return 4 instead of 1, so we can keep it as is, since it doesn't matter what we return in the case of the error, as long as it is not 0. Yeah. We can do actually one final test, so we make clean and default and compile all the stages. And that was it for today, so I hope that I will have time to expand the error handling, and that we will finally get at least some errors, so that the work on the compiler will be a bit easier. And this is where we finish today.